Good evening, coders. Since the MozCode is live, we're here with a new session on dynamic code. This can be performed in programs written in various programming languages C, C++, Java, Python, C hash, PHP, Erlang, and many others. So, why don't you come and update one knowledge about the same? Welcome to the live stream of Dynamically Coded with our speaker Rajat Jain, who is a software developer at Microsoft, is a learning advocate at egghead.io, JavaScript, an experienced mentor, a tech speaker, and highly skilled in Java, Python, and Android development. He is here today not as a motivational or inspirational speaker, but as someone who is looking to guide young minds on the step by step journey on achieving their definition of success. Over to you, sir.
Hey, thanks, Manya, for this nice introduction. And okay, I don't know if I'll not be giving you any motivational or inspiring lesson today, because ultimately that's what I give anytime I speak. So yeah, I mean that will be in the process. But thanks for the introduction. That pretty much sums it up. The product that I'm working on in Microsoft is Microsoft Teams. Um, it's a nice little buzz out there, and it's beating the hell out of Slack. So let's keep it up there. And then today we are going to talk about dynamic programming. So it is one of those concepts that when I was studying, when I was in college and doing competitive programming, this was something that used to challenge me a lot. I used to like it. I used to solve. I used to try a lot of DP problems, as dynamic programming in general. I mean, in short, is called DP. And I used to try a lot of DP problems because people say, my seniors used to say, and I've read it at a lot of places, that you cannot master DP just by learning how to solve DB problems. No, you have to solve as many questions as you can. So I'm not a supporter of quantity over quality, but in terms of DP problems, you have to make that exception. You have to solve as many questions as you can just to get that grasp in your head that how a problem, if it's given to you, how can you justify or how can you decide that it's a DP problem. And secondly, you have to be you have to understand and know how to solve it, because it doesn't comes to you or to your mind intuitively. So you have to reach at a stage. When I say you have to master DP, it means that you have to reach at a stage where just by looking at a problem, you're confident that it's a DP problem. And secondly, you are very much confident in creating the solution to it. I'm again saying it does not come intuitively in your head. If you are not able to solve any DP problem, don't be disheartened, because it's supposed. I mean, I'm not saying it's very hard and it's complex and you have to spend your day and night just by solving DP problems. It's not like that. It's like a general concept, but it's not intuitive. So in that area, you have to focus and you have to work a lot to make it intuitive to your brain. Okay, this is the introduction. Um, what today's session will be about is I'll be demystifying what dynamic programming is. I'll be telling you how to think a dynamic programming question. And again, I will be solving, just by telling you the basic concepts of DP, we'll be solving three or four odd questions. There'll be one question that every class of dynamic programming starts with, which is the nth Fibonacci sequence. So if there is a Fibonacci series, you have to tell me the nth Fibonacci number. The second, we'll go to a problem which is called the wine price problem. I'll talk about it. And third, we'll go to the naps. I think the coin change problem. And lastly, we'll end the session by solving the knapsack problem. Now these are very standard problems, and you should know how to solve these. I'm not saying that these will be asked to you or you'll be solving these kind of questions quite often. Maybe not. But by solving these basic questions, and particularly with DP, this is a great thing that if you let's say there are a set of 20-25 questions which are really fundamental and really good questions in DP, the classic ones. If you have solved those 25, 30 problems, the classic ones, you will get the confidence to solve 50, 100 problems, because more or less other problems are just tweaks to these classic problems. There are some really good questions which are genuinely unique and novel, but at the same time, these 25, 30 questions are a must if you want to crack interviews of most companies. If you are done with these 25, 30 questions, you'll be confident, at least on a basic level. So we'll be doing the 4 questions after I teach you the concept of DP. So let me share my screen first for this. And Manya, you can tell me if it's visible.
Yes.
Is it visible?
Yes, so it's visible.
Okay. So, what is the buzz all about? Why is DP? Why are every seniors? So this is what used to happen in my college. So I was entering into my second year. In second year, people teach you. I mean, you get introduced to data structures and algorithms, and uh, there are college contests. And in those contests, there was always a question. Like for us, it would be a little bit easy, but at the same time, let's say there are 5 questions. After the third one, the fourth one would be a DP. And if you do not know anything about DP, you'll feel that okay, this problem can have many branches. I mean, this problem can go anywhere. It's diverging into a tree. Either you can take this item or you can't take this item. Either you can take the next item or you can't take the next item. So every time it's a 0-1 solution. And you'd feel like okay, I cannot solve it this way because it will go to an exponential time complexity, right? Every branch, if every item is branching into 2, and if there, let's say there are n items, so the time complexity would go to exponential. So what to do? And that's when we got introduced to DP. And the seniors also used to frighten us. They also used to scare us that okay, you have to wrap your heads around it, because the most essential aspect or the most essential element of DP is recursion. What is recursion? We'll talk about it. But recursion is not easily. I mean, it doesn't easily come to your head. It's you need to develop that sense of understanding to create a recursive solution. So that recursive solution understanding actually came when we got introduced to trees. So that's a lesson for you. Whenever you are preparing the best data structure to that you should, I mean, that after linked list is the very important data structure, but after linked list, trees should be the prime focus for you, because in trees, not just you are learning about trees and you're able to solve tree questions, at the same time you're learning recursion, because most of the tree questions are solved using recursion. They can be solved iteratively also, but it's easier through recursion. And now when you get the feel of it, it's quite easy for you to solve DP problems. Yeah, but the buzz is all about. So in all the interview questions, in all the interview rounds, let's say if there are 4 questions, third will be of a DP question. I mean, third or maybe fourth also will be a DP question. If there are 3 questions, the last one will be a DP question. If there are 2 questions, the second one will be a DP question. You cannot skip a DP question in any of your online coding rounds. Rarely it can happen, but most of the time it doesn't. So you cannot skip this. You can skip higher, advanced data structures sometimes, but dynamic programming, no, you cannot. So that is the reason for all the buzz. Today we are going to answer these questions. What is dynamic programming? Is it genuinely difficult to wrap your head around, or is it just a hoax? How can we know when a problem can be solved using dynamic programming approach? Is it important for interview purposes that I told you? And how can we master it? Okay, so I've already told you the second one. Yes, it's genuinely difficult to wrap your head around, but it can be done through practice. See, I love solving challenging problems. So for me, DP was something. I mean, when someone would say me that, okay, hey Rajat, I'm not able to solve this question, but I know it's a DP, and then Just by listening to that last sentence, I would just take it up, because I used to like solving DP, because initially I couldn't solve it. I used to sit in the morning, it used to be evening, and I'm not able to get it. Let's say this was in my second year, third semester, and that used to give me all the high, that I'm not able to solve it. But when I used to solve it, and I was able to solve it after evening, let's say it took me the entire day, and then that feeling was something great. If you are able to get the recursive solution, and trust me, if you are starting with DP, even if you are, let's say, a beginner, not a beginner, and you are at the intermediate level, you might relate to it. Whenever you get a good DP problem and you're able to get the recursive solution of it, if you're able to form that equation, it's a next level high. And I cannot explain you that. You will feel it once you start doing it. Is it important for interview purposes? Yes, I've told you it's very important. And the last one, how can we master it? Sadly, there is no tonic for that. There is nothing like, if you understand the concept, like for example, in most of the domains, people say that you shouldn't mug things up, right? And that's true. You should not remember things. You should be able to think a solution right at the spot. Completely agree. But when you start solving a problem and you keep on solving similar kind of problems a lot, sometimes it happens that it stays in your head. Now when a question comes and you're like, oh, I've solved it someplace, let's say it's a coin change problem, and you're like, yeah, I've solved it. It doesn't make you a cheater, it doesn't make you bad. You can remember questions, that's okay, because you are solving that much questions. You're not purposefully remembering it, intentionally remembering it, it's just in your head. That's how you'll master DP. You have to solve as many questions as possible. And um, uh, in the last slide, I have all my social media handles, mostly active on Twitter and Instagram. um, I'll be posting all those questions, all the links. Uh, they'll be mostly from an editor, a coding platform which was very popular back in the day when I was in first year. It's called Spoj, SPOJ, Sphere Online Judge. So I'll be posting all the DB problems from SPOJ, from Code Forces, from CodeChef. I have a list of all those on my Twitter and on my Instagram handle. So please check that out. And yeah, so in that way you can prepare. Now, what is dynamic programming? I've talked a lot about dynamic programming, right? uh, I've been using this word a lot right from the start. But what is it, and why is the word dynamic in it? So let's say you have a problem. Let's talk about Fibonacci, right? You have a problem which can be solved by so firstly, which can be broken down into smaller sub problems. Like for example, if I want to ask you what is the fifth Fibonacci number, you will tell me that it's the sum of the fourth and the third one. Now you have to get the fourth and the third one to get to the fifth. Now you come to the fourth one. Now if I want to get the fourth one, I need to know the third and the second. If I need to get the third one, I need to get the second and the first. So in that way, your bigger problem is being broken down into smaller problems, smaller sub problems. But you can ask me, Rajat, isn't this the thing that we do in divide and conquer? It's the same, right? In divide and conquer also, as the name suggests, you divide the bigger problem into smaller sub problems, and then you keep on solving them to conquer. Definitely, that's the way. That's how. That's the aspect in dynamic programming. You have to break it down, and then you have to solve the smaller ones and reach to the top. Perfectly agree. So, is dynamic programming same as divide and conquer? No, actually not. So there is an extra tadka. There's an extra element that you add to it. What is the extra element? The extra element is that, okay, if you are solving for Fibonacci of, if you want to get the fifth Fibonacci number, you want 4 and 3. If you get 3, let's say you get the third Fibonacci number. Now to get the fourth Fibonacci number, you have to again break it down to the third element and the second element. Now you have already calculated the value for the third Fibonacci element, so you can reuse it, right? That's the whole concept of dynamic programming. So it's divide and conquer, but with cache. You can save the uh, progress, whatever you have done, in some place, so that whenever that particular thing or that particular sub problem comes again, you just have the solution. So you don't have to solve everything again. You can just give it in order of one. That's the second aspect of dynamic programming, which is overlapping subproblems. So in dynamic programming, there are two concepts. First is optimal substructure, which means that if I want to get an optimal solution of this big problem, I have to divide it into sub problems. So firstly, I have to first get that whether it can be, if it can be divided into sub problems. Now, optimal substructure means if I get the solution of these sub problems optimally, I'll reach to the solution of the bigger, the major, the main problem. I'll reach to the optimal solution for that too. If I have optimal solutions for the sub problem, I'll eventually have an optimal solution for the bigger problem, the main problem. That is the first thing in dynamic programming, which is same as divide and conquer. But plus the memorization part. The second aspect is overlapping subproblems. As I told you in Fibonacci, and I'll explain it further. I'll show you the diagram, and that it'll be more clear to you. But the second aspect is overlapping subproblems. So to get rid of it, to get maximum advantage of overlapping subproblems, what we do is we save the data or the progress of that we already have in data structures like array or map or whatever it's your choice. Now you have that stored. Now whenever that problem comes again, because it's overlapping, you can just give it back. Why is it called dynamic? Dynamic means that, so most of the time whenever we are solving, we know that next this is going to happen, next this is going to happen, and then we devise our algorithm based on that. You can think of any problem for that. But let's say we're talking about dynamic programming. I have certain coins, and I want to create. Let's say I have 1 rupee coin, 2 rupee coin, and 3 rupee coin, 5 rupee coin, 1 2 5, and I want to and I have unlimited supply of 1, 2, and 5 rupee coins, and I want to get a total sum of 7. How can I get that? So there are multiple solutions to it. There can be a solution where I have just 1 rupee coins, like I have 7 1 rupee coins. There can be a solution where I have the 5 rupee coin and the 2 rupee coin. There can be a solution where I have 5 1 rupee coins and 1 2 rupee coin. There can be multiple solutions. You don't know. So let's say you pick the first one as the 1 rupee coin. Now you have multiple paths to take. You don't know where your code will go. You don't know where your approach will go. That makes it dynamic. You have taken the 1 rupee coin. Now you can take another 1 rupee coin, you can take a 2 rupee coin, or you can take a 5 rupee coin. So this is, just give me 1 minute, 1 moment. Yeah. So this is where the word dynamic comes in dynamic programming. So let's think about it. If I ask you, there is this problem where you have to do 1 plus 1 plus 1 plus 1 plus 1 plus 1. So what is the solution here? The solution is 7, right? Now if I ask you, what is the solution here? I'm just adding one more 1 to it. So you can immediately say 8. Why? Because you already had calculated the previous value, which is 7, and this 1 is added, and you just answer 8. This is the difference. You did not do 1 plus 1 plus 1 plus 1 plus 1 again. You had the solution stored, you just added a plus 1 to it. This is what dynamic programming is. It actually happens in our brain also. When I say we are not intuitively, whenever we think of a solution in an algorithmic solution to a problem, we do not intuitively go to DP, or we do not intuitively get a solution. Even if we know that it's a DP, we do not intuitively get a solution. We have to wrap our heads around it. But actually, our brain is doing the same. Our brain is doing saving a memory at the previous memory and just adding or just forming a solution on top of it. It's beautiful. So I read this really great quote today, which says that dynamic programming is basically recursion plus some common sense. What is that common sense? I already talked about it, right? What is that common sense? The common sense is storing the already resolved sub problems value. That's the common sense part of it. The much talked about nth Fibonacci number. So what's the Fibonacci sequence? It's a very common knowledge. Oh, I missed something. Okay, so it starts with 0, then it's a 1, and then 0 with 0 and 1, we form the rest of the sequence, which is 1 plus 0 is 1, then again comes 1, then 2 plus 1 is 3, 3 plus 2 is 5, 5 plus 3 is 8, 8 plus 5 13, 13 plus 8 21, and it goes like that. Now if I ask you to give me nth Fibonacci number, how will you do it? It's simple, right? You just have to calculate, you just have to iterate over it, and you have to just keep on summing the previous and the element just previous to the previous. Okay, but it does have a recursive solution, and people do it a lot. So let's think about the recursive solution. There is Fibonacci. So this is the main function, and we have a Fibonacci function where the base case is if n is equals to 0 or n is equals to 1. Again, sorry, there's a typo here. If n is equals to 0 and n is equals to 1, just return n. So if it's 0, return 0. If it's 1, return 1. Otherwise, return Fibonacci of n minus 1 plus n minus 2. Fibonacci of n minus 2. So basically, I'm calling these functions again. In the next slide, I'll be telling you, I'll be showing you the sequence of how it's executed. Okay, let's say I have 7. I want to get the 7th Fibonacci number. So when I call fib7, it ultimately calls fib6 plus fib5, right? So I mean, it has to sum both the values. So it calls fib6 and fib5. Do I have the value of fib6? No, I don't have. So it's further divided to fib5. I mean, it further calls fib5 and fib4. And when I say I'm making recursive calls, so which data structure is being used here for all the recursive calls? It's stack. So every recursive call that I make, it's stored in stack. So I'm using a memory space here. That's fine. Okay, let's say I'm using it. So I keep on dividing it. I keep on dividing it into two parts, calling two functions from every single function, and then ultimately when I reach 2 or 1, as I have said here, sorry, as I have said in my previous code snippet, that whenever I get, so it's a 1 base indexing, so it can be n equal to 1 or n equal to 2. Whenever it reaches n equal to 1 or 2, it returns n. So as soon as it reaches here, it just returns back with the number. Now fib3 have it. The fib3 has the number. Now it returns back to 5, returns back to 6, returns back to 6, and now whatever comes here and then comes here, they are added, and I'm given the 7th Fibonacci number. This is how basic recursion works. Now the problem is, if you analyze the complexity of this solution, it's order of n. Is it? No, it's order of 2 ki power n. Why? Because at every n, it's being divided into 2 parts. So 2 into 2 into 2 into 2 till n. So it's 2 ki power n. Can we come up with a solution better? Because as we know that in the order, if we have the order of time complexities from best to worst, exponential time complexity comes at the worst segment. So we have to improve it, right? So how do we improve it? See, here there's a fib5 that we are calculating. Now let's say if I have calculated fib 5, do I have to calculate it again? No, right? So let's say there was an array where I could store this value of fib 5, so that whenever it's called again, I can just return that value. Wouldn't it be nice? This whole tree will just vanish, because I don't have to iterate. I don't have to break it down into all these components, and it just returns the value in O1. That's the beauty, which we call memoization. It's not memorization, it's not memorizing, it's memoizing. Memoize means if you have a solution and if there is a state associated with it. So what is the state associated with it? The number. I'll save this particular solution in a store with this particular state. So I'll say that whenever 7 is the state of my problem, return it from the store. That's the memoization process. So what I do is, it's very simple. What I do is I just have a read only, I have a global cache array. And what I do is I initialize it with -1. This is the memset function. It's a function available in, I guess, algorithms library and algorithms header. And what it does is just I have, let's say, the maximum is the maximum limit is 100. So what I've done is, for all those 100 elements, I have added, for all those 100 memory spaces, I've added -1 in cache. So it has been initialized with -1. Now I'll check if cache of n is still -1, then go here. But if it's not -1, which means that cache of n has been calculated. So just return that. Do not go into this entire process of breaking it down into two further components. It's that simple. Memoization is just a process of storing the value that you have in a memory. Now, you can ask me that, Rajat, you are doing all these things. You are breaking it down into, you are going from the top, right? I'm going from n. It's at the top, it's n, and then I'm going to n-1 and n-2. Then from there, I going to further down. I'm calculating the value at the bottom, and then I'm going up again. But what if I could have just done like this, where I have a Fibonacci sequence. I'm just assigning, I'll have an array of 100 elements. I'll just assign the 0th and the first element as 0 and 1. And then whenever I'm asked the nth Fibonacci number, what I'll do is I'll iterate over from 2 to n, and then I'll keep on filling the values. That's it. Now, once I do it, now if I'm asked, it's not done here, but if I'm asked anything less than n, I already have a solution. And how can I do that? Just make Fibo as a global array. And if you are doing that, now if you are asked again with a number which is less than n, you already have a solution calculated for that. Beautiful, isn't it? So what is the bottom-up approach? So that was the top-down approach. What is the top-down approach? You have n, you go to n-1, n-2, you go to further down, till a point where you have the value. It's returned back at the top. That's the top to bottom approach. Now, what is the bottom-up approach? You have the value calculated for the smaller elements, the smaller indices, and then you kind of go to the top. That's the bottom-up approach. So it's a if I had to give you an example, it's like when you say that, okay, I'll first read the concepts of DP, then I'll go to code forces and solve all the problems, then I'll master it, then I'll sit for the placements. This is bottom-up approach. What is the top-down approach? Okay, I have to sit for the placements. For that, I'll have to master the DP problems. For that, I have to solve as many questions in code forces as possible. For that, I have to first understand the concept of DP. So this is coming from top to down. Both are okay. Both are equally, you can say, equally likely to happen. Both you can use both of them intermittently, whatever suits you. So for me, bottom-up approach doesn't come quite easily. For me, I always go towards the recursive solution, and the recursive solution is a top-down solution. So mostly I look forward to top-down solution. But if you are have solved a lot of problems using bottom-up, and that's what hits you whenever you see a problem, it's totally fine. You can go with the bottom-up approach. Steps to follow, it's as simple as that. For the top down, develop the recursive solution of the problem, memorize it, voila, that's it. There you go. If you're following the bottom approach, try the bottom approach. That's it. Because in the bottom approach, you already have, see, you already, in the bottom approach, you already have an array associated with it. You don't have to explicitly add on to it. Like, for example, in the top down, you have to have a recursive solution, and then you, for memoizing it, you add an array to it to memorize, to store the solution. But with bottom up approach, you start with an array, and then you kind of make it rise it to the top. Now in comes, let's say there was another state variable here. When I say state variable, it means the variable that is changing, right? So the and what is the time complexity here? It's order of n. It was order of 2 key power n over there. It was 2 raised to the power n, and I brought it down to order of n. How beautiful is that, right? So bringing it down from the exponential time complexity to the polynomial time complexity. Now let's say there were multiple states, and yeah, I was talking about state variables. What is a state variable? State variable is the variable that keeps on changing, the variable that your function depends on. So there can be multiple variables here, but always keep in mind that the number of variables that you have, that much you'll have to add as dimensions to your array. So if you have, let's say, two variables in the parameter here, let's say n and m, so your fibo would be a 2D array. It will not be a 1D array. So sometimes we always say, right, we often say that in DP we are decreasing the time complexity by at the cost of space complexity. Earlier we were not using any space, right? We were just using, I mean, we were using a space because we use recursion. So ultimately recursion uses stack, but explicitly we were not using any other space. So it was just that just exponential time complexity. Now we have reduced the time complexity, but at the cost of giving extra space. But that's fine, right? Because nowadays people discuss about space complexity a lot. I mean, in interviews you may be asked that, okay, solve this problem without taking an extra space. But at the same time, if you talk about real life scenarios, people do not think about space complexity anymore, because you have a phone with you which is having 120, which is let's say, okay, if we talk about working memory set, RAM, the phone is today is having 16 GB RAM, 12 GB RAM. That's huge. So right now memory is not a problem. The problem is time complexity. That's why DP rise as a solution. I already talked about optimal substructure and overlapping problems. Let me reiterate on that. What is an optimal substructure? So optimal substructure means if you have a bigger problem and you break it down into smaller problems, if you find optimal solutions to those smaller problems, ultimately you'll eventually reach to the bigger problem, and the solution that you have will be optimal. What is overlapping subproblems? As we saw in Fibonacci, um, I guess someone has his or her mic open. Can you mute
Uh,
yourself?
yeah, excuse me, sir. We have some comments, questions in the comment box. Would you like to take them?
Yeah, I mean, this will be the last slide, and then I'll take a 5 minutes question break. So there I'll be
What?
answering the questions. So what is overlapping subproblems? Overlapping subproblems mean that you have again a problem, you break it down into subproblems, but there are some subproblems which are overlapping. Like, for example, in Fibonacci, if you can see again, here this fib5, you had to solve for n is equals to 5, and here also you have to solve for n is equals to 5. If you solve it here, I mean, at once, if you have this fib of 5 calculated, you can memorize it, you can store it, and then here when the control comes here, and how will the control come here? I'll not go into detail there, but it's just normal recursive stack. So you can just go there, and you can just break it down whenever the function is being called, just create another branch. Whenever the function is being called, create another branch, and you'll be able to see that. So you calculate it, and once you can just return it whenever it's called again. Okay, I'll escape the slide, come back here, stop sharing. Yeah, okay, there are a lot of comments. Let me start. Okay.
So Abhay Sharma asks that how do you recognize if any question is of dynamic programming?
Okay, I'll come to that. Abhay, in a while. It's in one of the slides. I'll come to that. If you're not, even then, if you're not able to get it, if I'm not able to understand, make you understand it properly, you can again ask the question. Come again.
We
Sir,
have
instead
one
of
question.
yeah, sir, instead of recursive, if one goes from iterative approach where time complexity is on, should we still go for recursive? No issues there. I'm If we are saying iterative approach is the bottom up approach. So basically you're using DP, but you have thought of a solution which is bottom up, and you are going through that perfectly fine. The time complexity for the recursive one and the complexity for the this one, the bottom up approach, the one that you're saying, both will be the same. It's just a matter of fact what solution strikes you the first. That's it.
There's another from Ishan Rejra. How did your
Mhm.
interest develop in dynamic programming?
If you are good in if you have very much interest in problem solving, that's the what excites you. So okay, let me share a small story. So last week my manager asked me, what work do you want to do? I mean, we have these 20 tasks for the next quarter. What work interests you the most? And I said, in whatever task there is, you have a problem statement and nothing else, right? You have a problem statement, like, okay, this is the problem. There is no aage, there is no piche. This is the problem. Think of a solution, think of the feature that will serve the purpose, and everything you have to do. I mean, in my head I was like, oh, this is the best day of my life. So if you are a problem solver, if you like solving problems in real life or in coding exercises, you will ultimately get interested in DP, because DP will make you understand how our brain. It's somewhat philosophical, but yes, it will make you understand how your brain works. If you are really interested into DP, you'll get into that zone where you think that, okay, my brain also thinks like that. Okay, so whatever I'm doing here, whatever I'm coding, actually my brain is also thinking like that in my day-to-day problems. Just give me one moment. My Okay, just give me one moment.
Yes.
Yeah, sorry for the inconvenience. So I think I answered your question, Ishan, and thanks for asking the question. Which
Uh,
language most suited to time programming? See, it's an algorithm, right? So if you are doing competitive coding in C++, so most of the students in college, they do C++ or Java. So you can go with that. You can even code in JavaScript or Python, whatever suits you, man. It's just a matter of your choice. But mostly, if you are interviewing, I've heard this. I've not interviewed for Google, but I've heard this, that if you code in C++, they get impressed by it. So I think If you have already started doing, learning C, which most students do, then go with C, C++. Yeah. What is an ideal approach to take up dynamic programming? It's a quite vague question. Can you ask a better question? Slightly more concise and slightly more developed. Anirudh. Next. So please start teaching in VIT. so VIT has been the college where I have been the most. I've been to three of your hackathons, and I've been to the college for my younger brother. He passed out from VIT last year, so I've been to VIT a lot. I can't comment on your professors, but yes, thanks for the offer. What was asked in Microsoft interview? Okay, that Mozilla Firefox VIT. These people have to organize another talk for that. But I think I'll be giving this talk next week, sometime. How was my Microsoft experience and everything? So there you can have. Just follow me. I'm not again. Say, see, so sorry. I'm not saying to follow me anywhere if you want. If you don't want to, but if you want to, and if you want to get regular updates, if you want to just know stuff, please follow me. Yeah. Nothing. All done.
So I guess that's it. You can end this.
Okay, perfect. I'm again sharing the screen. Now in the next part, we'll be coding. So that'll be interesting. So this is where you understand or you recognize if it's a DP problem or not. So see, first of all, if you have solved, let's say 50, 60 problems, time programming questions, you'll have this knack. And this goes with everybody, right? This is not like if you're smart enough or if you are your IQ is this much. No, all that is bullshit. If you have solved as many questions in DP, like 50, 60 problems, you start getting a knack. For that matter, anything, right? If you keep on doing anything, that thing, you develop a knack for that. If a carpenter is cutting wood, he knows that how much pressure to apply, and how if he wants to cut a wood in a certain pattern and in a certain different pattern, how to do it, everything. If he does that quite often, same goes for DP. So then you'll understand. But secondly, if you want to get a tip, or if you want to get a pointer on how to recognize if it's a DP problem, mostly DP problems are categorized into two. Broadly categorized into two types. First is optimization. Here you are asked to minimize or maximize a certain output. So we'll be solving the knapsack problem. We'll be solving the wine price problem. Both of them will focus on optimization. So let me tell you the problem statement of knapsack, and that's really interesting. Manya, you can tell me if this is visible.
Okay.
Okay, so let's say you are a thief. You are a thief. You have come to a house.
It's not visible.
Sorry, it's not visible.
Uh, yeah, like it needs to be shifted a little.
Okay. Okay, let me tell it. Okay. Let's say you are a thief. Let's say you are a thief and you have come to a house. Sorry. You are a thief. You have come to a house where you see a lot of jewelry and flower vase, gold. Everything is there. Now, everything has an associated price with it. But you have a bag which can take only 11 kgs. Now, what is the situation? You are a thief, you enter into a house, you see a lot of things lying around, and you want to steal everything. But the problem is, the restriction is that you cannot. And because you have a bag, a knapsack, which is the bag, it can store only 11 kgs. Now, there are, let's say, 10 items, and each item has a price and a weight. You are given all these values. Every item has a price and a weight. Now you have to tell the thief what all items he should steal such that he gets the maximum price out of those stolen goods, but and he is able to store all that in that 11 kgs bag. So the weight of the goods that he will steal should not cross 11 kgs, but having that restriction of 11 kgs, he should be able to maximize his stolen goods price. Now that is something which will come under optimization. So you have a restriction, but you have to optimize. Will get you'll get more confident and more comfortable with it once you start solving problems. I'll give you a list of problems. I'll share it at a different place. Maybe I'll share it with the Moz Club also, and I'll share it on my Twitter or Instagram handle. Then comes the second uh, category, which is combinatorial. What is combinatorial? We all have studied, right? We all have been through 11th and 12th, and we all have done the PNC, permutation and combination. So in permutation and combination, what happens is, let's say you are a teacher, you have to give you have 14 candies, and you have 20 students, and you have to give those 14 candies to 20 students. How many ways there can be where you will be able to distribute those 14 candies to 20 students? All the students are distinct. You can give either student 1, or you cannot give student 1. You can give a candy to student 2, or maybe you cannot, maybe you don't. So there are choices. But in PNC, we just have to give the answer. It can be I'm not sure what is the answer. I mean, it should be 20C14, but I'm saying that if it's polynomial complexity also, but you just have to give the answer. You have to give 2 key power something. That's the answer, right? But here we have to do it through code. We cannot go through, we cannot go to an exponential time complexity. So how can we do it? Now in this knapsack problem only, it can have a slight glimpse of combinatorics also. So how is it? So there are, I told you, right, there are let's say 10 good items, 10 goods having different prices and weights. Now either you can take the first one, or you cannot, or you don't. Either you take the second one, or you don't. Either you take the third one, or you don't. So you have choices. So maybe till now in your head you have a tree forming. If he takes the first item, if he doesn't take the first item, now let's say the first item has been chosen. If he takes the second item, if he doesn't take the second item, and then if the first item itself was not chosen, will he take the second item? If he doesn't take the second item, so it is a tree that's being formed, and every time it's the thief has 2 choices. Every time the thief has 2 choices, so we have the complexity as order of 2 raised to power n, and we have to decrease that order. How will we decrease it? We can decrease it using memoization by storing the value, the solution, the answer to one of the sub problems, to all the sub problems basically, because it will be overlap. The first problem, the wine price problem. So let's first understand what the problem is. It's a big problem. It's an easy to understand problem. Not easy to understand in the code perspective, but easy to understand as a problem. So before I read all that, let me make you understand what the problem is. Let's say you have 10 wine bottles lying around. You have 10 wine bottles. Do not read the problem, first understand. You have 10 wine bottles. Every bottle has a price associated with it. So every bottle has got a tag. Now you have to take the wine bottle. You can take from either the left side or the right side. So you can take the leftmost bottle or the rightmost bottle. But every time you take it, the price gets multiplied by the iteration number. So for example, you are taking it for the first time. Let's say I take the left one. So if I take the left one, and its price is 50 rupees, it will be 15 to 1. Now let's say I take the left one again, and its price is 20 rupees. So it will be 20 into 2, because it's the second number in the iteration. So now let's say I take the rightmost one. So now the value will be first into 1, second into 2, and then this rightmost one into 3. So every time you take it, it keeps on multiplying the number with the iteration count. Now you have to get the maximum profit out of it. You're selling it. You're not buying it, you're selling the items. So you have 10 wine bottles, every wine bottle has a price tag. You are selling it to people. The only reason, I mean, the restrictions are that you can sell either the leftmost bottle or the rightmost bottle. Every time you sell the bottle, you sell it with on a value which is price of that bottle into the iteration count, the on which iteration you are selling it to. Now read the question. Imagine you have a collection of wine bottle placed next to each other on a shelf. For simplicity, let the number of wines from left to right, and they're standing in the shelf integers 1 to n. So there are n wine bottles. Because the wine gets better every year. Suppose today is the year. So when I'm saying iteration count, they're saying every year you are selling one wine bottle, and with the passing year, every year the price gets multiplied by the year that you are selling it in. So because the wine gets better every year, supposing today is year 1, so the price on year y, the price of the ith wine will be y into the price of the ith wine. That's what I told you. You have to sell everything. So what is the maximum profit you can get if you sell the wines in optimal order? So let's say this is the wine price 23514. Okay. So now when I read this question, when I read this question for the first time in, I guess, in my 4th semester, I think. So immediately when you see this, you get confused and you think it's a greedy problem. What is a greedy problem, by the way? What is greedy? Again, the names, as it goes by the name, greedy means you think of a trick and you choose something just because on basis of your greed. So here, what I think is, I'll sell the bottle with maximum number of with the maximum price later in the year, so that I get the maximum price. So let's say if I sell the bottle number 4 in the first year, I'll just get 4 into 1. But if I sell it in third year, I'll get 4 into 3, 12. So what I thought was, okay, every time whosoever is less, just sell that bottle, because it keeps on increasing, the year keeps on increasing. So in the last, only the bigger bottle will be left, and I'll sell that for, I mean, multiplied by the larger year number, and I'll have the maximum amount. Fair enough. So what I did was, I started doing 2 into 1. So I first sold the second one, then I sold the third one, then I sold the fourth one, because after 2 and 3, now between 5 and 4, I just can sell the leftmost and the rightmost one. So after 2 and 3, 5, between 5 and 4, fourth one is the is the least pricey one. Then comes 1, and then lastly I'll sell the 5. So what will be the price total? 2 into 1 plus 3 into 2 plus 4 into 3 plus 1 into 4 plus 5 into 5, which is 49. Perfectly agree. But if I would have sold it in this way, I would have sold the P1 first, so 2 into 1. Then I would have sold the fourth one, so 2 first, then 4, then 1, then 3, then 5. Okay, so 2 first, then 4, then 1, then 3, then 5, which is of no order, right? It's not at all whatever I was thinking. It is not at all based on the low and the high price. It's completely random order. But when I choose that, the sum makes 50. So this came as a surprise to me. I was like, okay, this seemed like a greedy solution. This seemed like an easy solution where whatever is the less, just sell it, and then ultimately you'll be left with the bigger one, the one with a larger price. And now the year has also been, the number of years has been passed by, and it's also at a greater value. Ultimately, it'll make the whole thing greater, but it is not like that. So what can be it? So if you do not know how to do it, if you do not know what path to go, you just make a tree, right? So let's say in the first iteration you can choose either 2 or 4. So if so you'll have two paths with 2 selected, with 4 selected. Let's say you selected 2. Now you have either you can select 3 or you can select 4. But if you selected 4, you could have, now you can select 2 or you can select 1. So in that way your tree will form. And now we all know that where we are heading towards. We are heading towards dynamic programming. So let's do this. Let's create a function, the recursive solution. So first, just leave this base case. If I, let's say, choose the, so and it has got three values: the beginning index, the ending index, and the year, which is right now. So I'll start it with 0, n minus 1, and the first year will be 1. So I'll start, so in the calling code section I'll be calling solution with 0, n minus 1, and 1. Now price 1 means one, so I have a tree, right? So the, let's say, one path can be, I choose the beginning one multiplied with the year, so this will be my price, plus I'll call it with be plus 1, because I have sold the, I've sold the beginning one, so the index will be be plus 1, en will be, the ending index will be the same, and now year will be year plus 1. Second path can be, I will sell the ending index, so price en into whatever year it is, plus I'll again call the solution with be, as in the beginning will not change, ending will be reduced. Now the last bottle has been sold, so it will be en minus 1, and then year plus 1. And I just have to do a max of price 1 comma price 2. And a recursive solution should have a base case, because ultimately otherwise it will just go and keep on going on and on. So the base case will be if the beginning index and the end index, if they cross over each other. So if beginning index becomes greater than the ending index, so basically you have just crossed the entire, you have just iterated over the entire array, the price array. If it is like that, then return 0. So it'll keep on calling functions, and keep on adding the value, and ultimately when it'll reach the last, it'll just return with 0. So ultimately whatever will be added, and lastly a 0 will be added, and this will be price 1, this will be price 2, and you just have to return the maximum of price 1 comma price 2. That's it. This is the DP solution. This is the recursive solution, not the DP solution. This is the recursive solution. Okay. Choosing the leftmost item, choosing the rightmost item, and returning the max price. I know if you are not familiar with recursion, if you have just started, it will not feel very intuitive. Again, I'm using the word because it is not. You have to be comfortable with recursion before you jump into DP. Otherwise, you will just leave competitive programming. Maybe you will be leaving computer science also, because you have to understand this, that there are certain, so if you do not have the ground floor, you cannot have the first floor, right? If you, without having the ground floor, you create a first floor, it'll just, your house will collapse. So that's why you should be very familiar with recursion and how the entire tree structure forms, or how every call creates a function call in stack. If you understand all that, maybe I'll post a video about it, or something, some resource about it. But if you know about that, things will be easier for you. Now, this is not a DP solution. This is just a recursive solution. How do I make it a DP solution? By memoizing it. But before that, I have 3 state variables here. Can I reduce them to 2? Do I need 3 state variables? Can I calculate year from B and En? I can, right? B is on the first, En is at the last. If I take the difference, it is n minus 1. And if I subtract it with the total number, I'll get the current year. Let's say I increase the B with this much. Now, whatever is the difference between B and En, if I subtract it with n, I'll get 2, because I've taken 1. So I don't need actually year. So what I can do is, I can just remove year from the equation, from the solution, from the parameters. And what I'll do is I'll calculate it here, and then I'll use it here. Okay, this is the first thing that we can do. Why I did that? Because ultimately, if I know that something can be reduced, I mean, some state can be calculated using the other two states, I can just remove that. Because ultimately, I need to have a cache, right? I need to have a cache that I'll be storing the subproblems value in, the subproblem solutions value in. So if it is three states, I'll have to create a 3D DP, a 3D array, which will take a lot of space. So how, if I can reduce it, I should. Now this is the final solution. This is the DP solution where I have a recursive solution. I'm memoizing it and I'm putting it in front of you. Now this is a top-down approach again. To see the to look into the bottom approach, you can go and check out Hacker Earth or Geeks for Geeks. But this is the top-down approach.
I guess there is some issue. We'll continue in a while.
I'm audible.
Yes, sir.
Sorry, there was a power cut. I'll share the screen again.
Never mind. So, yes.
And Manya, please tell me if there is a lag in my voice and my audio and my video.
Uh, yes, sir, sure.
Okay, sharing it again. Yeah. So I had a recursive solution. Now I'm memoizing it using a 2D array. Why a 2D array? Because uh, I have to keep a state, right? I'll say that if this is B, if this particular value is of B and this particular value is of En, then I have a solution. So cache of, let's say, B is 2, En is 3, and let's say I've calculated the value of 2 comma 3. So I'll just say cache 2 comma 3 is 2 cache 2 3 is available, and I'll just return that. That's why I need to have a 2D DP, a 2D array. Sorry. So I'll initialize it with -1 again. It's the basic procedure. I initialize with -1, and I'll say that if B in greater than En, return 0. If cache of B and En is not equal to -1, which means that it has been calculated before, return cache B En. Otherwise, return now whatever the value of max bn comma max price1 comma price2 is. I'll just store it in cache ben. So if this gets calculated, its value will change from -1 to that particular value. And if it that particular sub problem hits again, I'll just return the value in the cache. So it's simple. So we iterated over three solutions. First, this is the basic recursive solution. Secondly, we reduce the number of states, and this is a nice approach, where we should think of reducing the number of states. If we can derive a particular state from the other states, we can do that. We should do that. The third one is the final DP solution, where I have a recursive solution, but I memoize it such that I can use it for later purposes for the different subproblems. Now comes the coin change problem. So the two DP subproblem, the two DP category of problems were optimization and combinatorial. So this was an optimization problem. Now let's see a combinatorial problem. Combinatorial means you are asked the total number of ways to do a particular thing. So what is the coin chain problem? It's simple. As I told you, you have certain rupee coins, certain value coins. Like for example, you have coins of 8 and now this is the coins, this is the value of coins that you have, and you can have you have unlimited number of 8 rupee coins, you have unlimited number of 3 rupee coins, you have unlimited number of 1 rupee coin, and unlimited number of 2 rupee coins. Now you have to create a sum of 3. How can you create that? Either you can take 3 1 rupee coins, or you can take a 1 rupee coin and a 2 rupee coin, or you can take a 3 rupee coin. That's it. So there are 3 ways where you can in which you can use these 4 coins to create a sum of 3. So that's the problem. How many number of ways? So given an amount and a denominations of coin available, determine how many ways this change can made for amount. There's limitless supply of each coin type. So let us go to this particular problem. Okay, so this is the problem. Let's solve it. Okay, I'll do it live. So given an amount and the denomination of the coins available, determine how many ways change can be made to amount. Yeah, the same question. Now what I can do is, oh, okay, I have a solution because okay, so I maybe solved it. Okay, so let's go over the solution then. This is my gateways function. What I'm doing is I am creating let's forget this for once. Let us go step by step. First create a recursive solution and then we'll memorize it. So let's forget this line for a while. This gateways method calls solution, which takes in n. N is total the sum that I want to achieve. C is the vector, the list of all the coins, and then I'm passing c dot size also. Okay, why I'm passing c dot size and why I'm passing n and why I'm passing c, we'll get to know. So what I want to do is, okay, let's make it sum. It'll be better then. This is the sum that I want to achieve. See, this is the live example of how a bad naming convention can screw you up. So always use good naming convention. It'll help you understand the code better. Anyways, so I keep on distributing gyan like this. So you have a solution wherein you have a sum. So what I'll do is, why did I take this sum? I took this sum because every time I select a particular coin, I'll reduce that particular value from this sum, and I'll check whenever sum becomes 0. It means that I have ultimately it's a tree, right? So it keeps on going down, 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 and when the sum reaches 0, it means that that particular path where the sum is 0, the leaf node is 0. So that particular path has actually returned a solution. Is actually one way of doing whatever I'm trying to achieve. So whenever sum is equals to 0, return 1. 1 means this is the path. Ultimately, this path will make the sum 0, which means I started with sum. If I am reaching 0, which means this entire path, if I sum the values of this path, I'll reach this particular value. So this is one right path, so I'll return 1. Why I'm returning 1? Because ultimately it will be adding on to the solutions. So 1 will be added. So if this is one path and one path, I have got one path, I've got one way, I'll return 1. Now if n is less than 0, no solution exists. So if I'm saying that if so it should be sum also. So if sum equal to 0, return 1. If sum is less than 0, so let's say I keep on decreasing the sum, but at certain point sum becomes less than 0, which means that no, this path doesn't work. So just return 0 from there. Do not keep on subtracting it. So at a certain point, if in my tree, if in my path, If sum becomes 0, just return from there. If sum becomes less than 0, just return from there. It that path is now no longer valid. Now, if size is less than 0, I mean, you can just remove this check. This is just an extra check that if size is less than equal to 0, like there are no coins, and if I'm asked a sum, let's say I have no coins, but I'm asked a sum, so it should return 0 directly. Just right now, just do not look at this. What should be, just remove this. So what should be my normal solution, recursive solution? If I take the first one, I'll subtract its value from sum. And yeah, why did I take size? This is a nice question. So why did I take size? What I'm doing is I don't want to take index. What I'm doing is I'll just take this size minus one value, and I'll decrease the size. I'm not starting from 0. I could have done like that also. So I could have started from 0. I could have put index here, and here I could have just put 0. Means that I'm starting from 0 and I'm going till the size of the array. But what I did instead was I started from size, the last one, and I kept on decreasing. It's the same thing. So let's say if I take I take the size minus one element, because I can take it again, I'll not reduce the size, but I'll reduce the value from sum. So this is my first solution. Solution is sum minus c of size minus 1 comma c comma size. So I took the last value, but I did not reduce the size because as we have seen in the problem, I can use as many ones, I can use as many twos. So I don't want to reduce the size here because I can still use the size minus 1 value. Okay, so this is one solution. And the second solution, and then the second path can be I do not take that value. So if I do not take that value, if I don't want to take, like for example, in this case, in the first case, yeah, in this case, this 8, I don't want to take it. So what I can do is whenever that 8 comes, I'll just return. I'll not return. I just make my size as size minus 1. So I have two paths. If I choose it, then I'll reduce the sum and I'll not reduce the size because I can again choose it. If I don't choose it, if I don't want to choose it, so I can just keep the sum as it is and I can decrease the size by 1. So I do not want the last element to be chosen. Simple. That's it. Now this is a recursive solution. What can be the memory solution for this, the DP solution for this? I have, and now, okay. Why do I have a 2D array? Here there are 3 parameters. I told you, right? We
Excuse
only
me,
put,
sir. Sorry to
yeah,
interrupt. Sir, your voice is
yeah.
lagging a bit.
Okay. That's what I was worried about. Just give me one moment.
Yes.
I'll just switch on to a different network.
Yes. I guess there's some issue.
Yeah. I'm audible now.
Yes.
Is there a lag?
Not yet.
Okay, perfect. There won't be. If there's a power cut, maybe there's some issue over here. So yeah, just bear me
No
for
issue.
that. Uh, Let me share my screen again. Can you look at my screen?
Yes. Yes.
Okay, sure. So yeah, that's it. And now we have to memorize it. So what I did was, yeah, I was telling why I have a 2D array and not a 3D. I have 3 variables here. But if you see, this second one is just a read-only thing. I'm not changing it. This particular thing is just giving me information. I want to use C. That's why I'm having it. But this is not changing at all. This is not a state variable. State is something that keeps on changing. So my changing things are sum and size only. That's why when I'm storing something, I'll have these two values only, because C is just a dummy over there. It's just there for providing us information. Whenever I want to access a particular thing, I just use C. Other than that, I keep on changing sum and size. So my entire tree depends on sum and size. That's why I have a 2D value. And how do I decide this range? This is an inefficient way of doing this. You should use malloc, but excuse me, doesn't matter in competitive coding. So that's what we used to do, and I don't want to dig deep into that. That's why I'm just using 251 here, because as you can see, the limit is 250. Limit is 250. Okay. So that's about it. This was the coin change problem. Again, let us reiterate on this. What is the coin change problem? What is the problem? First thing, you have certain values, certain denominations of coins. Let's say you have a 1 rupee coin, a 2 rupee coin, and a 5 rupee coin, and let's say an 8 rupee coin, and you need to create, and you need to reach a sum of, let's say, 50 rupees. How many paths are there to reach a sum of 50 rupees? You can use as many number of coins as possible, because you have a limitless supply of all the coins. So what you can do is, either you have to take a coin or you don't. If you don't take a coin, you just increase your index, or or if you are using the size value, you're using the size value, you can just decrease the size. If you want to use it, so use it, decrease it from the sum, and then do not increase or decrease the size value, because you can again use it. So there will be two paths always, and ultimately it will be an exponential time complexity. But now I want to use DP, so I need to optimize this recursive solution that I have. So how do I optimize it? I use memoization. Using memoization is very easy. Just have a global array or anything. It can be a map also, depending on the circumstances. It doesn't always suit, but having an array is easier. And then if you have that particular value already existing, if for this sum and for this size, if I have a value which is not equal to -1, because I initialize it with -1, right? If it's not equal to -1, just return that particular value, and that entire tree will be pruned. So it will be just over here. As soon as I get us at a point where there is a sum and a size, and for that the DP, the 2D array value is not -1, it will not go down. It will just return the value from there in O1. Okay, I've submitted this code. This has passed, so there's no issue there. Then comes the knapsack problem again. And you must be wondering that I am not at all looking at the bottom up approach. I'm always focusing on recursion. The thing is, having I want to teach you recursion. I want you to think in recursive terms, because I'm not saying recursion is a better approach, or you should not at all use the bottom up approach. The bottom up approach is a tabulation approach. You already have a 2DDP stuff. Like, for example, in the coin change problem, if you're using if you were using a bottom up approach, you'd have a 2D array, and then you would have started filling it from the 0th index, and then you kind of create that entire 2D array, and the final element is the solution in this case. So I'm not telling you all that. You can read it, or you can watch video tutorials for that. I want you to understand recursion or understand recursive solutions, because it will help you a lot in your later life. Like, I do front end in Microsoft, but at times there are functions where I have to use recursion a lot. Let's say I'm working on a tool, and which keeps on. So let's say I'm working on a tool which keeps on opening up I have a JSON object. Sorry, I know there are students from college, but let's say if someone understands JSON object, or think of it as an accordion. There are websites, right? You click on it and it opens up. So let's say I have a tree like structure wherein I click on something and it opens up, then I again click on that opened up thing, it opens up, and I need to perform operations on each of them. So it's a it feels a recursion, right? And it can be done using recursion. It has an iterative approach also. But if you know recursive solution, iterative solution is this much, recursive solution is this much. That's why I'm focusing more on recursive solution, because you need to understand, you need to create that understanding in your head, because it will help you a lot. Coming back to our knapsack problem, the original problem that we had. What is that problem? The problem is that you have a thief. You are a thief. You enter into a house. You see a lot of items over there. Every item has got a price and a weight. Now you have to steal as many items as possible. I mean, as pricey items as possible, to increase that overall stolen goods price value. But at the same time, you have a bag which has a weight restriction. It cannot exceed, let's say, 11 kgs. So if you cannot exceed 11 kgs, so you have to pick items in such a way, in order to maximize your overall profit, and not increase the not tearing out your bag. So your bag should be intact, because you are a thief. You should have a proper heist, a successful heist. um, that's the question. I cannot keep on iterating over it. So let's solve it. I have it open somewhere. Okay, yeah, this is the problem. um, n is 3, so this is the number of items that you have. Weight is 4, so this is the maximum weight that your bag can that your knapsack, the bag, can hold. So these are the values of all the items. Values as in these are the prices of all the items, 1 2 3, and this is the weight of all the items, 4 5 1. What should be the output? Output should be the maximum price that you can pick. Okay, now this problem is not yet solved, so let me solve this for you. So what are the variables here? The variable is the total weight that we have. So what I want to do is, in every time, but whenever I'm selecting something, I'll just keep on minus something. So whenever I'll call this knapsack again, I'll just do knapsack w minus something, because let's say I've chosen something. This weight will just be this is just dummy, right? This is just giving me information. Same goes for value. Weight and value are just dummies. And then n is the total number of items that I have. So if I select one item, right, n is the total number of items that I have, right? If I select one item, I can reduce the size of it. So let's say I chose the n minus 1th item, and then I reduce the size of the total number of items to n minus 1. So I can take, I already took that item, let's say. So there are some items. I can take an item, or I can leave that item. I can take another item, or maybe I leave that item also. So there are two paths always. So how do I do this? So what I do is, I'll do return. Let's say I take the n minus 1 item. So I'll say return w minus weight of n minus 1 item. I just decrease the weight from w, that particular item. These two are just dummies, and then I reduce the size. Either this, or so I need to get the maximum profit, right? So whenever I do this, there'll be a profit value that will be added, right? So it will be the profit value if I took the n minus 1 item. It will be val of n minus 1. So this will be the value that will be added, and then knapsack will again be called with, now w has been reduced, wt value n minus 1. This is one this is one part of the tree. The second part will be, let's say I do not take that item at all, so there'll be no addition to the price. I'll just call knapsack again with same weight. Both these two are just dummy arrays, and now I just don't want to take that item, so the value will be decreased, but there will be no addition to the price. That's it. That's a recursive solution. That's it. Now you have to add the base cases, right? So what should be the base case? If w equal to 0, which means what? If w equal to 0 means what? Just give me a moment. Yeah. If w equal to 0 means what? It means that you have reached the particular place where the weight is 0, which means that particular path uh, actually it can be included in the solution. So if the weight is 0, which means return 0. You don't want to add anything there. If weight is 0, which means the path is finished. If weight is 0, you don't want to add anything. So just return 0. If, can there be another condition? If n is, so, and weight can also go negative, so just return 0 over there. If n becomes 0, n becomes negative, because n keeps on reducing, right? So yeah, n is return 0. Anything else? What can be other solution? What can be other solution as in other base cases? Can there be other base cases? So there is w. If w is less than equal to 0, which means that I have reached the end of the tree, just return back with no other value over there. If n is less than equal to 0, return 0. That's it. That's it. So this is the solution. This is the, you see, and now again, if you went through bottom up, it would have been this bigger code. I mean, at least 40 lines of code, at least double this. But now with recursion, it's just one line of code with some base cases. But yeah, this is what's just one line of code. I have to reiterate. I may have to reiterate on the base cases. We'll do that later. Now, is this a DP solution? No, this is just a recursive solution. Let's go to DP solution. So what are the state variables here? State variable is w and n, because these two are changing and nothing else. So what I do is, whatever is the upper limit of w is 1000, n is also 1000. So 111. Just to be on the safer side, I take one extra, because sometimes doing some operation, maybe you fucked up, sorry, whether sometimes you can mess up somewhere, and you can mess up somewhere and you can just exceed the bound. So just to be safe, I take one extra, and then after this, what I'll do is I'll say if dp of w n not equal to -1, return dp of w n. Okay, I think I won't be able to submit it here because they are not letting me go into this and change this driver code. Anyways, you understand the just right. So if it's not equal to -1, and in the main I'll just have a dp array and assign it to -1, all the values to -1. Anyways, so I'll return this. Otherwise, I'll return dp of wn equal to this. See, if you don't want to do it, you can just do it like this. dp of w1 is like this. Return dp of wn. It's the same. That's it. That's your solution. Either you can take a value, if either you can take an item or you cannot take the item. If you take that item, you need to decrease its weight from the total weight, because now you have filled it in your bag, and you have to add to that, add its value to your solution. So you add the value to the solution, then you again call the knapsack with the decreased weight and the decreased number of items. Or the second solution can be you don't want to take that item at all. So what you can do is you can just not decrease the weight and just decrease the item value and do not add anything to the solution. Like here you added the value, and whatever is the max of both the paths will be returned, saved in wn, and you can return that wn. This is, again, I'm retreating on it. this will become more intuitive to you if you are very much acquainted with recursion. And how will you get acquainted with recursion a lot? Just keep on solving. So the best exercise is by solving 3 questions. For your interview preparations, for internship or for final year placements, you have to prepare. You have to go through 3 questions because it's asked a lot. Inverting a binary tree, or mirroring a tree, or get the height of the tree, or get the left view of the tree. There are a lot of questions, but all those questions feel very easy when you get the hang of recursion. So you keep on solving them and you get better at recursion, and then while solving DP, you'll feel a little bit comfortable, a lot comfortable actually. But yeah, I think this was it. Finally, if you want to look at the key properties that whatever we understood, whatever we learned today, it's breaking a problem down into subproblems. Then the subproblems are overlapping and recurring. So using memoization, we'll store the values and reuse them. Sacrifice space complexity to get polynomial time complexity. Earlier it's exponential time complexity, but we sacrifice space complexity. Why do we sacrifice? Because we are adding another array, a 2D or a 1D or a 3D array, just to get things done. So that's why we are sacrificing space complexity to get better time complexity, to get polynomial time complexity. Examples are n Fibonacci, knapsack, longest common subsequence, longest increasing subsequence, coin change, rod break problem. There are a whole lot of problems. I'll share that. These are the platforms where I'm very much active on. This is the Instagram handle that I was talking about, JavaScript Rescue. But I also share other content also there. And yes, let's connect. Thank you. Manya, I think we'll take questions from here now.
Yes. So we just have one question that can you explain the recursion line in which the program which you were explaining?
Come again?
So the program which you were explaining, so we have a problem from Guru that can you explain the recursion line?
The last one? The last problem that I was explaining, right?
Yes.
Okay. Let me go to that problem again. And let me use my board here. Can you see my screen?
Not yet. Sir.
Now?
Yeah.
Okay. Let me bring it a little bit closer. Oh, okay. So let me tell you what is the value. 1, 2, 3, 4, 5, 1. Manya, you can tell me if it's visible.
Yes, sir, it's visible.
So this is the price array. This is the weight array. Maximum weight that can be stored in that knapsack is 3. Okay, this is the value that we have right now. So let us construct the tree out of it. Let's construct the recursive tree out of it. Recursion tree. So first thing, if I choose it or if I don't choose it, right? So let's say this is the first one. First item, I choose it. So if I choose it, I put a 1 over there. If I don't choose it, I put a 0 over there. Okay. So let's say I choose it. So if I choose it, the total value will be 1 plus something. If I don't choose it, the value will not be, there will be no addition to the value. It will just be removed. So now here the array will be 2, 3 for me now. Perfect. Now here I again call for 2 comma 3. I again call 1 0. Either I can take 2 or I cannot. Okay. Okay. But at the same time, when I chose 1, my total W, which was 3, now from 3, my total weight can only be 3, and I chose a weight which was 4. So as I know that whenever W, and so whenever I take this, I do a W minus weight of 1. Weight of 1 is 4. So W minus 4, W is 3. So this becomes negative. Whenever I say W is negative, I return 0. So on this path, there will be nothing. So this will just return 0. So there can be no path where 1 will be chosen. So 1 cannot be chosen at all. There can be no path where 1 is chosen. So let me do this. Okay. Here, what I can do is, if, let me do it here directly, if weight of n minus 1 is greater than W, return directly dp of wn as, so if it's greater than W, then there is no need of doing all this, right? I can just do this. To return here again, just to maintain the similarity. So if, so for me, this in this first, if I chose 1, I could have never done that because its value is 4. 4 in itself is greater than 3. So I have said that if weight of n minus 1 is greater than W, return knapsack W weight n minus 1. So I just remove this. And let's say I'm not iterating from the last element, I'm iterating from the first element. It doesn't make any difference. So I remove 1. Now, all the path that would have occurred in that tree from choosing 1 is now gone. It's all null and void. Now the path is if I do not choose 1. So now this tree will focus on. Now comes the second one. See, I'm looking at the wrong example. Let me look at this example, 451. 451. Okay. Now come to the second one. Either I can choose the second one or I can not choose the second one. But see, if I choose the second one, the weight is again 5, which is greater than 3. So this entire tree gets pruned away. So only this part is now active. So I did not choose 1. I did not choose 2. Now comes 3. Can I choose it? Yes, I can choose it because this value is less than maximum weight. So let me choose it. So if I choose 3, what is the value that gets added? 3 plus, now knapsack will be called with W minus, what was the W? 3 minus iska weight. What is this weight? 1. So now W will it will be called with 2 comma weight comma val comma, I don't know if it's visible or not, weight comma val comma, what will be the final thing? What is the final thing? N, right? So n will be, now I've reached the end, so n will be greater than 3. Obviously n will be 4, let's say. I'm not decreasing, I'm increasing. Let's assume that I'm increasing from 0 to n. So n will become 4, and now ultimately this will reach a point where I'll say that n has reached its limit, so it'll return 0. So this whole thing now will return 0. So the final solution will be 3. So whenever this returns something, it returns 3 here, it returns 3 here, and ultimately on the top where the answer has to be printed, it will be 3. So the answer becomes 3. Now this was simple because in both these cases I could just prune the tree because it is greater than the value. So this addition is actually solving a lot of problems. This addition is actually optimizing the solution a lot more because there can be values which are directly greater than W. So if there is a value which is greater than W, and I'm not saying W, I'm not saying this W, I'm saying, let's say you keep on decreasing W and you reach a point where W is 4, and there is and your next item that you are going to discuss upon or that you're going to analyze is of weight 50. Will you try and go another level just by decreasing 4 and making weight as 4 minus 50? No, you can just see it's 50, my current weight is 4, it cannot be accommodated, just leave it. Just call this and do not go here. See, here it's returning only, right? So it will not come here only, it will just return from here. I think I've made it a little bit better. I think so. If it's not, then whosoever asked this can ask it again, and I'll again explain it. Maybe, sorry, maybe on some document online, as in I can show you by using a pen. Anything else?
Yes, sir, we have a question that is there any way to improve problem solving skills outside of coding, or is practice enough?
Problem solving in a, I mean, yeah, you have to do practice. So, okay, let me tell you what I used to do. I used to so back when I had in the formative years, like in my second year was my formative year. Third year also, in the first semester, it was completely formative for me because I'm a slow learner. So I'm a slow learner. It was all formative for me till fifth semester. Then after fifth semester, I got to know a lot. I got to learn a lot. Then I started I kept on practicing the entire second year and my until fifth semester. But at a certain point, you know that you have done some questions. Now you need to do some more questions. I mean, the tougher questions. You keep on participating in contests. So even if there is no contest over there, you can just create another a virtual contest on lead code or on code forces. I used to use code forces. So I used to create a virtual contest and then sit for 3 hours, try to solve whatever questions I can. If not, I could just spend the entire day just by looking into problems, just by solving problems. So there are two motivations for this. If there's a question like this, I don't know, if someone asks for motivation, I don't feel motivated about doing competitive programming or DSA, where I'm not able to solve questions. I leave it, and then ultimately that question is left forever. What should be the motivation? What should drive me? See, there are two things. I can tell you two things that can drive your inner motivation for doing solving problems in DSA or competitive programming. One, it's very important for interview. It's if you are a fresher, if you are in college, to crack campus interviews or off campus interviews as a fresher, even as an experienced developer, if you are in backend, um, DSA problems are a must. In college level, you are asked tougher questions. When you are at a certain level, you are at a certain experience. DSA questions are mostly straightforward. Even then, they are good questions, but mostly classic questions, straightforward questions. But in college, they can ask you. There are companies like DirectEye. There are companies like Rubrik. Companies like Amazon, Goldman. I'd not put Goldman into this a lot, but these companies ask questions, very tough questions, in their first online round. And when I say tough, I do not mean tough if you have prepared, but I mean tough if you are just solving questions for fun and not actually analyzing what you are not solving. Let's say I am about to solve 4 questions. I'm set to solve these 4 questions in a contest. I could solve 2 questions. Then I went ahead. I mean, I went with my friends partying and all, and I just left those 2 last questions. That won't help. You need to be able to solve good questions also. So if you're not able to solve a question, solve it again. Keep practicing over it, thinking of a solution. In initial days, you can just spend days. There was one problem, I spent a week on it and I couldn't solve it. Then ultimately, I had to resort to an editorial for that. Now there's a solution. There's a difference between editorial and solution. In editorial, you are told how to do a problem, what is the concept behind it. But in solution, it just gives you that damn code. Do not look at the code. Look at the editorial. Think of what you were missing, and then write code yourself. So the first motivation is interview. The second motivation is, even if you are in a company and you want to switch, you have to do it again. Ask me. uh, I have been doing it, not because I want to switch, but because I always want to be at the edge. Like, आज मेरे को मन किया कि काम नहीं करना, कंपनी में छोड़ना है. आई शुड नॉट बी फीलिंग लाइक, अरे मैंने तो प्रिपरेशन ही नहीं किया, फक मेरे को प्रिपेयर करना पड़ेगा, आई नीड टू प्लान 6 months and all. No, I keep on solving these questions on a daily basis, like 1-2 questions on a daily basis for the past 6 months. Why? Because I always want to be on the edge. Why? Because I like solving questions. So whenever I find time, my life is very sad. I keep on. I am Whenever I find time, I go to lead code. That's me, but that's different. Um, so if you spend time in college, if you are really practicing it hard in college, it will be beneficial for you in future also, I think.
So we have one last question.
Yeah.
That does the selection of top approach or bottom approach affect the effectiveness and the complexity of the algorithm?
In my entire in the entire set of questions that I have ever came across in the DP domain, there has been one problem, I don't recollect it, where the bottom up approach was better. Other than that, in terms of, I'm forgetting that particular caveat, but in terms of, I mean, in general, if I want to generalize it, no. And I'll stress more on this. Try getting into the top down approach more, because it'll help you a lot in, not just in DP, it'll help you a lot in many other domains. So if you are if you train your mind to think in recursive way, it'll help you. But yeah, no issues if you are solving a question, and if you have come up with a bottom up approach, why not solve it?
So that was it.
Thank you.
Thank you so much. And on behalf of all the members of Mozilla Firefox Club and the attendees of the webinar, we sincerely express our gratitude towards Mr. Rajat Jain for his inspiring words of guidance, which we hope answers some of the participants' questions regarding competitive coding and provides them with a better picture of MozCode. His words have encouraged us to code with passion and provided a direction to our curious minds. I would further like to thank all our attendees for being such an amazing and supportive audience. We sincerely hope that all of you have gained some valuable knowledge from our esteemed guests and taken away something new from our event. This was Manya Garg signing off. We'll meet you again in the next webinar session. Have a great night. Thank you so much,
Bye.
sir.
Yeah, thank you. Bye.